All right, let's get started. So this is section 7.3, Pythagorean Theorem, even though we really won't be doing the 7.3 homework out of our Big Ideas textbook. Today, you guys will be doing a worksheet that has Pythagorean Theorem questions on it, and the worksheet will refer to the problems like that we have in the notes today. And then tomorrow, we're going to take Pythagorean Theorem to the next level. We're going to do a section from the geometry, high school geometry textbook, and it's going to have us, as I mentioned last time, writing our answers as simplified square roots or radicals. And I'll explain what that means tomorrow. There won't be any of that today. We're just going to learn the basics of the Pythagorean theorem today. So Pythagoras was a Greek mathematician and philosopher, as most mathematicians were back in the day, trying to figure out why things worked. So you studied math. Who discovered one of the most famous theorems in mathematics, or at least he's the one who wrote it down. It was actually discovered before his time. I think ancient Egyptian tablets have proven this was used in other parts of the world before Pythagoras, but he was the one who got famous for writing it down. Back in the day, if you wrote something down, you were the one who claimed credit for it. And it lasted the test of time because tablets can break. In mathematics, a theorem is a rule that's been proven to always be true. The theorem that Pythagoras discovered is called the Pythagorean Theorem, and here's what the Pythagorean Theorem states. In a right triangle. Now, do you know what kind of triangle a right triangle is?
Yes.
You should. We did that a couple chapters ago, right? In a right triangle, the sum of the squares of the lengths of the legs. That was a lot of ofs, so I'm going to restart. In a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. And so I need to define some words here. You saw legs and you saw hypotenuse. In a right triangle, there are three sides, obviously. The two sides that make up the right angle are called legs. Always the two sides that make up the right angle. They don't always go vertical and horizontal. You can rotate a triangle, as we have a few chapters ago. It's the two sides that make up the 90-degree angle. Those are called the legs. They're the two shorter sides, because in a triangle, the largest side is always across from the largest angle. And since the right angle is the largest angle, the hypotenuse will always be the longest side of a right triangle. And you'll always find it across from or opposite from the right angle. Okay. Can you get the door for me, Shane? Lizzie, you had a question? No? Okay. Now, we call the legs A and B, and we call the hypotenuse C. I don't care which leg you call A and which leg you call B, but the hypotenuse has to be C. So this equation here is exactly taking this paragraph or this sentence here, this exact sentence in equation form. When it says in a right triangle, the sum of the squares of the lengths of the legs, when it says the sum of the squares, we're referring to a squared and b squared. Okay, so the sum of a squared and b squared is equal to c squared. That is actually an astonishing statement to make, because that helps you find the missing side of a right triangle if you only know two of them. Okay, if you have two sides of a right triangle, doesn't matter if it's A and B, A and C, B and C. Okay, whatever two sides you have, you can use those two sides to find the third leg in a right triangle. And so back in ancient times, because you're building pyramids and other buildings that have to have corners, right angled corners, they would use the Pythagorean theorem to make sure they had right angles, because the Pythagorean theorem, if it's true, you have a right triangle, you have a right angle. Okay, so they would use, actually, the legend has it, I think it's been written down, they had a piece of rope and they would tie 12 knots in the rope, one at each end, and then I guess 10 in the middle. They're all equidistant apart. And if they folded the rope over to where there was 3 knots on one side, 4 knots on the other side, and 5 knots on the hypotenuse, it always made a 90-degree angle. Okay, we'll learn about tomorrow, actually not tomorrow, we'll learn on Friday that that's called a Pythagorean triple, and a 3, 4, 5 right triangle is your first Pythagorean triple. Okay, we'll talk more about those later, but let's talk about the basics for today. Do you believe that this is true? Because I said it's true? Because Pythagoras said it's true? There are literally hundreds of proofs for the Pythagorean theorem. I'm going to show you a few of them, including the waterproof, and the next video I'm going to show you is actually a slide proof to show you this is true. I'm going to show you some videos that can do it more justice than what I can. So Shane, can you get the lights for me, please? And your attention needs to be up here on the board. Okay. See if I can share the right screen.
What do Euclid, 12-year-old Einstein, and American President James Garfield have in common? They all came up with elegant proofs for the famous Pythagorean theorem, the rule that says for a right triangle, the square of one side plus the square of the other side is equal to the square of the hypotenuse. In other words, a squared plus b squared equals c squared. This statement is one of the most fundamental rules of geometry and the basis for practical applications like constructing stable buildings and triangulating GPS coordinates. The theorem is named for Pythagoras, a Greek philosopher and mathematician in the 6th century BC, but it was known more than 1,000 years earlier. A Babylonian tablet from around 1800 BC lists 15 sets of numbers that satisfy the theorem. Some historians speculate that ancient Egyptian surveyors used one such set of numbers, 3, 4, 5, to make square corners. The theory is that surveyors could stretch a knotted rope with 12 equal segments to form a triangle with sides of length 3, 4, and 5. According to the converse of the Pythagorean theorem, that has to make a right triangle, and therefore a square corner. And the earliest known Indian mathematical texts, written between 800 and 600 BC, state that a rope stretched across the diagonal of a square produces a square twice as large as the original one. That relationship can be derived from the Pythagorean theorem. But how do we know that the theorem is true for every right triangle on a flat surface, not just the ones these mathematicians and surveyors knew about? Because we can prove it. Proofs use existing mathematical rules and logic to demonstrate that a theorem must hold true all the time. One classic proof, often attributed to Pythagoras himself, uses a strategy called proof by rearrangement. Take 4 identical right triangles with side lengths A and B and hypotenuse length C. Arrange them so that their hypotenuses form a tilted square. The area of that square is C squared. Now rearrange the triangles into 2 rectangles, leaving smaller squares on either side. The areas of those squares are A squared and B squared. Here's the key. The total area of the figure didn't change, and the areas of the triangles didn't change. So the empty space in one, C squared, must be equal to the empty space in the other, A squared plus B squared. Another proof comes from a fellow Greek mathematician, Euclid, and was also stumbled upon almost 2,000 years later by 12-year-old Einstein. This proof divides one right triangle into 2 others and uses the principle that if the corresponding angles of 2 triangles are the same, the ratio of their sides is the same too.
Hey, we learned
so
that
for
this year.
these 3 similar triangles, you can write these expressions for their sides. Next, rearrange the terms.
Cross multiply.
And finally, add the 2 equations together and simplify to get AB squared plus AC squared equals BC squared, or A squared plus B squared equals C squared. Here's one that uses tessellation, a repeating geometric pattern, For a more visual proof, can you see how it works? Pause the video if you'd like some time to think about it. Here's the answer. The dark gray square is a squared, and the light gray one is b squared. The one outlined in blue is c squared. Each blue outlined square contains the pieces of exactly one dark and one light gray square, proving the Pythagorean theorem again. And if you'd really like to convince yourself, you could build a turntable with 3 square boxes of equal depth connected to each other around a right triangle. If you fill the largest square with water and spin the turntable, the water from the large square will perfectly fill the 2 smaller ones. The Pythagorean theorem has more than 350 proofs and counting, ranging from brilliant to obscure. Can you add your own to the mix? Did you enjoy this lesson? If so, please consider some.
So the proof that she just brought up is called the water proof. And so one of them I want to share with you, and this is someone who actually did this at like a science fair kind of thing. Let me share my screen again each time to do it. Here we go. So right now, a squared and b squared are filled up with water. And c squared fills up a squared and b squared. So there are more applications to the Pythagorean theorem other than just finding the missing side of a right triangle. Being able to, especially if you're in construction.
The University of Cincinnati Online. Oh,
sorry. Even if you're in construction and you're trying to make sure you have right angles, right? Because obviously if your building doesn't have right angles, if you're building a 4-sided building without right angles, you're having an issue. You're building a parallelogram. Have you ever taken a cardboard box and smashed it down flat? Right, and then you try to put it back up. If it's bent a little bit, it's a lot less stable, I should say, than what it is when it was actually before it was broken down. Right, when it had those solid right angles, it's just firmer and more solid. There's another one here. This one's just kind of fun. If I remember right, I think this one's the one with a nice little tune to it that kind of gets stuck in your head. Thank goodness for the drums. It's just funny because like someone took like separate shots. Like these are like pictures like compiled together with green sticky notes and yellow sticky notes. think you get the idea of it. Now there's also, can you think of a candy that comes in square form? Starbursts. You can find a starburst proof. You could actually do something similar to what they did with the sticky notes, and you could prove the Pythagorean theorem using starbursts. Now, all the right triangles you've seen in these videos have been 3, 4, 5 right triangles. She mentioned Pythagorean triples in her video, the first video we watched. And so Pythagorean triples, we'll talk about them later this week. But 3, 4, 5 is the very first Pythagorean triple that satisfies. Those are 3 whole numbers that satisfy the Pythagorean theorem. Xander, did I lose you back there?
Yeah.
Okay, sit up for me. All right. Let's go back to our notes then. Shane, can you turn the lights back on before I lose anybody else?
You're about to lose me.
Now, I think in one of my earlier classes with you guys, I mentioned this book right here, Euclid's Book of the Elements. They mentioned Euclid as the one who proved the Pythagorean theorem using what was probably the most confusing of the proofs, which was the corresponding side lengths, right, of the similar triangles. And so he spends roughly 200 pages, 150 pages of his first book proving the Pythagorean theorem by proving that this is, if this is true, this is true. If this is true, this is true. If this is true, this is true. Until finally he gets to a squared plus b squared equals c squared. Now he doesn't say a squared plus b squared. He talks about the segment BC squared and segment BA squared and that kind of thing. So, but that was a course I took in geometry, and that really opened my eyes to the Pythagorean theorem. I was like, for whatever reason, I was surprised. I had no idea where the class was going, and all of a sudden, like the last week, we closed with Pythagorean theorem. I'm like, that's why I learned all this stuff, because that's what he did. Euclid was is known as like the father of modern geometry. Yes. So the Pythagorean theorem, Pythagorean triples work in multiples. So if 3, 4, 5 is a Pythagorean triple, then 6, 8, 10 is also a Pythagorean triple if you times each of those by 2, or if you times them by 3 or 4 or 5. 3, 4, 5 is not the only Pythagorean triple. Another common one is 5, 12, 13. And then that works in multiples as well. Yeah, so there's a lot of Pythagorean triples, but it's actually an exclusive club because most numbers aren't going to satisfy Pythagorean theorem. All right, so in a right triangle, the legs, is there another space there? It shouldn't be. No, okay, just looked weird. The legs are the shorter sides, and the hypotenuse is the longest side. And as I mentioned before, it's always across from the right angle. Let's practice using the Pythagorean theorem to find a missing side length on a right triangle. One of the basic and most boring things you can do with the Pythagorean theorem, because there's so much cooler things you could possibly do that we won't get into this class. So the first things first, I need to write my Pythagorean theorem down, and it says a squared plus b squared equals c squared. That is the Pythagorean theorem. That's all you need to really memorize, as long as you know a and b are the legs and c is the hypotenuse. So I don't care if you write 5 squared in place of a squared or 12 squared in place of a squared, because you're just going to end up adding those two together. So again, it doesn't really matter which leg you call A and which leg you call B, but you do have to square them. This is why it's nice to know your perfect squares. These are two of the lower ones you probably already knew though. Jimmy, what's 5 squared? Okay, and what's 12 squared? Okay, so 25, oops, I put equals, plus 144 equals c squared. I combine my like terms. You can't combine the 5 and the 12 before you square them, just so you know, you have to square them first. What is 25 plus 144? Lizzie? That's right. Oh, that sounds like a perfect square to me. Lizzie, what is the square root of 169? 13. So the opposite of squaring a number is square rooting it, and that's how we're going to get c by itself, and that's going to give us 13 meters. Don't forget to label your side lengths that were in meters for question A. that make sense?
Yes.
Okay. Let's do it for question B. Oh, by the way, 5, 12, 13, that was one of those Pythagorean triples we just talked about. If you have decimals or fractions, we don't call that a Pythagorean triple. Pythagorean triples, we reserve those for the whole numbers that satisfy the Pythagorean theorem. Can negative numbers satisfy the Pythagorean theorem? I mean, I guess they could, because when you square a negative number, don't you get a positive number?
Yeah.
But what does it mean if you have a negative side length?
It doesn't exist.
It doesn't, yeah, exactly. You can't have a triangle as negative side lengths. So although a negative number could satisfy the Pythagorean theorem, no such triangle is going to exist. Let's do example B. We're missing A, so A squared plus the other leg. What's the other leg, Deegan? The 2.1 or the 2.9? What's the other leg? The 2.1, exactly. So A squared plus 2.1 squared is going to equal the hypotenuse, always across from the right angle, 2.9 squared. So that's our C, that's our B. All right, calculators at the ready. Martin, can you tell me what 2.1 squared is? All right, 4.41. Did you know that when you multiply a decimal with another decimal, it's going to have as many decimal places as there are decimal places in total? So if I'm multiplying a number that has one decimal place with a number that has two, it's going to have 3 decimal places. Does this make sense? You guys should know this from multiplying decimals. So therefore, if I'm squaring 2.1 and 2.1 has 1 decimal place and 2.1, the other 2.1 has 1 decimal place, my answer is going to have 2. Why am I saying this? Because if you know that, that's just 21 squared. 21 squared is 441, right? So do 21 squared, they have 2 decimal places, 4.41. Okay. Another reason knowing your perfect squares is handy. Now, I didn't have you go up to 29. So what's 2.9 squared? I don't expect anyone to know this off the top of their head. Brady? 8.41. All right. So we then subtract the 4.41 over to the other side. 8.41 minus 4.41 is just 4. I didn't write the subtraction down. I hope you can follow along with that. And we are now going to square root both sides again. And what is the square root of 4?
2.
It is 2. So A is 2 centimeters. A is 2 centimeters. So really, when you're using the Pythagorean theorem, you have 2 types of problems. Problems in which you're missing the hypotenuse, which means you add the sums together and square root. I said add the sums. That's a bit redundant. You add the squares together to get a sum, and then you square root. Or there are problems where you're missing one of the legs, like we just had in the last example, which means you're going to have to subtract that leg squared over to the other side before you square root. Okay? So you do them a little bit differently, but as long as you're solving the equation, you shouldn't have any issues. Go ahead and try C and D on your own, please. Go ahead and try C and D on your own. I'm going to pause the video and I'll give you some time to do that while it's paused. I apparently didn't put pause. There, nope. There we go. Yes, Deegan? Yes. Don't forget to label. These are just side lengths, so we're not doing, meters squared or anything like that. These are just side lengths, so you're just labeling with whatever units they're giving you. This is one of the most fundamental theorems. Now, that word theorem, I'm going to use it a lot this chapter. I used it a lot a couple chapters ago. We talked about the triangle sum theorem, the triangle inequality theorem. And so that word theorem is just something that's been proven over and over to be true in geometry. As soon as you prove it not to be true, then it crumbles and dies. And theorems, fortunately, have never been proven. Well, it's like never. The ones that have lasted the test of time are always true. You can say, I think this is always going to work, and then you find out it doesn't. Well, that's not a theorem. That's just you being dumb.
Do you think there'll ever be a time where they disprove the Pythagorean theorem?
Maybe in a different multiverse. The Pythagorean theorem wouldn't work, maybe. Yes.
Something so many times at that point, it's just kind of impossible like disprove it because there's already so much proof.
Yeah, and disproving.
Enough proof against it.
Disproving something is a way to prove something. So some proofs go the route of disproof. We're trying to disprove it and you can't do it. So then by default, it has been proven. Right. So it's actually one of the ways you could. You're right. That's people thought about that. And what if I can bring counter examples that wouldn't work and well, they can't find it. When you take geometry in 10th grade, no, 9th grade, it's 10th grade level, but when you guys take it as freshmen in high school, you will be writing proofs. Sure, maybe one's of the Pythagorean theorem. There are other things you have to prove. Do you remember the problem we had where there was like a river and there was two similar triangles and they wanted to know what the distance across the river was? And we said because that angle is vertical from that angle, so I know they're the same. And if I can prove those two are the same, these two are right angles, I know what that's a visual sort of proof. So you would say this is 15 meters because this. You list all the reasons you know that. That is your proof. And so you, in geometry, one of the big things you have to do in geometry is you have to prove why what you're stating is correct. Yes. Oh. Shh. No one knows about the fraction button on the calculator. Brady, do you have an answer or question? Okay, I'm going to go ahead and unpause the video now. Oh my goodness. Are you kidding me? I didn't pause the video. I stopped sharing. No, wait, that's not true. Yeah, I think it is actually. Yikes, I don't think I ever paused the video. Sorry, guys. Sorry for whoever's watching the video. I don't think I paused it. I'm sure you probably know when you fast forwarded. All right, example C. We are missing C. C is the hypotenuse. So Brady, what did you do to find C? Wait a second. 15, I was going to do 8 squared plus 15 squared equals C squared. Can I do that? Yeah, I could totally do that, right? It doesn't matter which leg you call A and which leg you call B. You're just going to square them and add them. So what'd you get for 15 squared? Brady knows that because he knows those 25 perfect squares. He's done them. Have you done yours?
I've done mine.
What's 8 squared? 64. And then Brady, what did you get when you squared 220? Sorry, when you added 225 and 64? Brady knows 289 is a perfect square because he's done his perfect squares. Brady, when you square root 289, what will you get?
17.
Yep, 17 feet. There you go. All right. So 8, 15, 17 is a Pythagorean triple because they're whole numbers that satisfy the Pythagorean theorem. Let's see if this one's a Pythagorean triple. I'm missing one of the legs. Maddox, you want to walk me through this problem? How would I set it up? Okay. Okay, so he said that the 16 has to be our other leg. Yeah, it matters which one we put here because I can't interchange these. One of them's the hypotenuse and one of them's the other leg, and it matters where you put those into the equation. What do you have for 16 squared? 256. That's one of your perfect squares, isn't it? Okay, and 34 squared is one of your perfect squares, right?
No.
Huh, thankfully not. What did you get for 34 squared? 1,156. Okay. And then what'd you do? Okay, what'd you get? And the square root of 900 is 30. That's right. So this is another Pythagorean triple. What's my label, Maddox? 30 what? 30 yards. Yeah. This is another Pythagorean triple, the 16, 30, 34. And actually, funny enough, This is the same Pythagorean triple as the previous problem, the 8, 15, 17. It's just all been multiplied by 2. Instead of 8, 15, 17, it's 16, 30, 34. So it's the same Pythagorean triple, just a multiple of it. Shane.
Is that how you want us to write it on the
Yes. Yes.
Did it with 34 squared minus 16 squared?
So you didn't plug it into the equation. You just started moving things around. Don't rewrite anything right now if you've already started it. Okay. Yes, Lizzie.
If you would told us it's the same triangle, you would just.
If I would have told you that, but I did not. All right, E and F, and then we've got a couple story problems we'll look at. E and F, I guarantee E and F are not Pythagorean triples because Pythagorean triples don't have decimals or fractions. They're just whole numbers that satisfy the Pythagorean Pythagorean theorem, but we can still do these problems. We're missing one of the legs. The other leg would be the 9.6, so I'm going to square that one. One of the common mistakes with the Pythagorean theorem isn't mixing up the hypotenuse in a leg, although I've seen that happen a couple times. It's forgetting to square the 9.6 when you put it in there and forgetting to square the 10.4. I'll have some students that just subtract 10.4 and 9.6 right away. You have to square them first, then subtract, not subtract and then square. It does not work the other way around. What is 9.6 squared? Anybody shout it out? Thank you. 0.16 and 10.4 squared. 108.16. I subtract 108.16 minus 92.16. Another common mistake I see is people subtract it and then circle their answer. Subtract it, and that's your a squared. We want a. So when you subtract that, what are they? 16 apart. Okay. And then when you square root it on both sides, you get a equals 4 what? Meters. Okay. So if your work doesn't look like mine, that's okay. I'm not going to, if you've already started your worksheet, I'm not going to make you redo anything. As long as you're showing your work. This is how I plug things in. Now, as we get into later in the week, we start doing the converse of the Pythagorean theorem. You're going to want to write it like this. So eventually it gets to the point you're writing it like this, even if you're not showing. And I'm really not showing a ton of work. I'm showing what I plugged in. I guess what you could do is just like skip to this step here, right? If you just want to go ahead and square the stuff, I mean, that would save you a step. But other than that, I'm really not doing anything. Like I'm not just writing all my work. I'm doing multiple steps at the same time, I feel like. All right, example F. My two legs are what I have. So 2/5 squared. That's my a squared or b, whatever you want to call it. Plus 3/10 squared. Put your fractions in parentheses. Put your fractions in parentheses. Equals c squared. When you square a fraction, you have to put it in parentheses. Otherwise, the square only applies to the numerator of that fraction. We don't want that. We want to make sure the entire fraction is being squared. We want 2/5 times 2/5, not 2 times 2 over 5. Do you remember how when we square rooted a fraction, I told you that you square root the top number, square root the bottom number? Okay. Well, when you square a fraction, you square the top number and square the bottom number as well. And you knew that whether you knew that or not. Because even if you would have written 2/5 times 2/5 or known that you just square it, you're still doing 2 squared and 5 squared. So if nothing else, maybe that proves why when you reverse it and square root it, that's why you're allowed to just square root the top and square root the bottom, instead of having to turn it to a decimal and then square. Which hopefully when I grade your guys' quizzes, I'll see that you did it the correct way instead of turning it into a decimal and trying to square root that, because that doesn't prove that you know how to square a fraction. It proves that you know how to use a calculator. We're going to get 4/25 plus 9/100 equals c squared. Now, the only issue with fractions is we would need a common denominator. Sky? Exactly. So we're going to multiply the first fraction to make by 4/4 to make it 16/100. To make it 25/100. What's 25 over 100 reduced to? Dawson? 1/4. Sorry, I'm like writing all over the place. Now we're going to square root both sides. And as I just mentioned, square rooting fraction is squaring the top of the fraction. What's 1 squared? Sorry, what's the square root of 1? 1. And what's the square root of 4? 2. And we're in inches. So half an inch. Yeah, I like decimals better. All right, let's move to our 2-story problems. You are playing capture the flag. You are 50 yards north and 20 yards east of your team's base. The other team's base is 80 yards north and 60 yards east of your base. How far are you from the other team's base? So let's say that each of these little grid squares are 10 yards by 10 yards. So if it says you are 50 yards north of your base, that means you are right there. Well, no, that's actually not where you're at. That's how far north you are. And then you are 20 yards east of that. So you're right there. That's you. Or Carter Shannon, if you just want to put Carter Shannon. That's where Carter's at. Okay. It says the other team's base is 80 yards north and 60 yards east of your base. Okay. So we already did 50 yards north. So 80 yards north would be another 30 yards north. And we've already done 20 yards east. Now we have to do another 30 yards, no, 40 yards. 2, 3, 4. 2, 3, 6. I want to say that's right. Does that look right? I'm like trying to count and make sure my lines are dotted and everything. So I believe that would be 80 yards north and 60 yards east of our base. So this is their base. And it wants to know what your distance is from their base. So now what I want you to do is I want you to draw a line that connects those 2 points. And we have to find the distance of that line. How would we find the distance of that line using the Pythagorean theorem? Xander?
Would make a triangle going up 30 yards. Or yeah.
Does that work? You could do either way. You're right. You could do it that way, right? Same thing. Okay. So what are the legs of that right triangle? How about 40 and 30? Remember, they're each 10 yards, right?
Yeah.
So 40 yards and 30 yards. And so we need to find the hypotenuse. Any guesses as to what it would be before doing the math? Owen? 50 yards. Remember that first Pythagorean triple we mentioned, the 3, 4, 5? This is just a multiple of 10. So real quick, if I prove it to you by doing the math, 30 squared plus 40 squared equals c squared. We'll just call it c. It's hypotenuse, right? It's across from the right angle. On the coordinate plane, you have plenty of right angles. So 900 plus 1600 equals c squared. So 2500 equals c squared. Square root that, and you're going to get 50 yards. That's correct. We knew that because of the Pythagorean triple. And the last one, which, by the way, that is what we will be doing on Friday. On Friday, we'll be using the distance formula. Instead of me giving you like a 50 yards east and 20 yards west, I'm going to say, I need you to find the distance between -3, 6 and 9, -12. And you're going to use a version of the Pythagorean theorem called the distance formula to find out how long that line is. And since the Pythagorean theorem is full of right angles, you're going to see a lot of Pythagorean theorem in the distance formula. A guy wire is attached 24 feet above ground level on a telephone pole that provides support for the pole. I read that wrong. Find the length of the wire when it meets the ground. 10 feet from the base of the pole. Okay, so the guy wire meets the ground 10 feet away from the base of the pole. So there's my right angle, and that's 10 feet. it says it's attached 24 feet above ground level. So from where it's attached right there to the ground, it's 24 feet. What are we missing? A leg or a hypotenuse? Sky? That's right. So if our Pythagorean theorem says a squared plus b squared equals c squared, which you don't need to write it every time, especially since it's pretty easy to memorize, you're going to plug in 10 for one of the legs, 24 for the other leg. What's 10 squared? 100. For those of you who done your perfect squares, what's 24 squared? 576 equals c squared. That's 676 equals c squared. Can someone tell me what the square root of 676 is? Awesome. 26. Oh, so now you know the 26th perfect square. 676, and that's gonna be 600, or sorry, 26 feet. Now on tonight's homework worksheet, which I'm gonna hand you, it says round to the nearest 10th. You're not always gonna get 26 feet as your answer. You might get 26.4 feet. You might have to round. So go ahead and round. It's double-sided, 5 questions on the front and 5 on the back. Grab one on your way out. Cards, go ahead, one on the way out. I see you.